Lying at the cores of most large galaxies, do we find the largest type of object in the universe, an engine black hole of supermassive size and stature. They almost always have masses many millions of times greater than the Sun, while the biggest grow to tens of billions. So large, in fact, that their event horizons would swallow the orbit of Neptune if placed at the centre of the solar system. These incomparable sizes underpin one of our universe's most intriguing mysteries, for no black hole should be anywhere near this large if it started out as a collapsing star. And yet, we see supermassive black holes of bewildering sizes scattered around the cosmos, including at the heart of almost every galaxy. Exactly what was responsible for seeding these great engines and catapulting them to their immense sizes is a mystery only the James Webb Telescope can shed new light on. And so, in our final outing of 2024, we will be examining its findings as we tell the story of supermassive black holes, unravelling the mysteries of the universe's most massive objects. Perhaps only 100 million years after the universe was born, primordial atoms of hydrogen and helium were shuffling around in the darkness as they were drawn together by gravity, in a snowballing process which ignited the first stars. These Genesis stars at the cosmic dawn probably took the form of massive, unstable bodies many dozens of times the size of the Sun. With no metal content to regulate the burning of their nuclear furnaces, these enormous hydrogen stars then rapidly began to blow in the first blinding supernova explosions. Given their considerable masses, it's likely that the first crop of stellar black holes would have followed in their wake, only a few million years later. And it is plausible that these black holes may have been the original seeds that were sown into supermassive engines, like the one lying at the heart of the Milky Way galaxy. But alas, even the oldest stellar black holes make relatively unsuitable candidates for the source of galactic engines, because the way in which they feed should severely limit their masses. A stellar black hole feeds largely through accretion, as particles under the greatest strain from its tidal forces orbit the body within a dense disk of frictionally heated matter. These accretion disks radiate explosive amounts of energy and particles, yielding a pressure that can dispel dust and gas further out. As such, if a black hole accretes too much matter and radiates too intensely in turn, then it may stifle its feeding in the long run by dispersing its supply of gas. In order to feed consistently over 13.8 billion years, those earliest stellar black holes at the cosmic dawn would have needed to accrete below their respective Eddington limits, the level of luminosity at which radiation pressure starts to overcome the force of gravity. And when applying such constraints, even the oldest stellar black holes would weigh just a few dozen solar masses today, barely a dent in the tens of billions of suns seen in the largest galactic engines. Clearly, there were other, more significant mechanisms at play in the early universe, which seeded supermassive black holes with their immense masses. Such mechanisms may predate the cosmic dawn altogether, ensuing only 1 second after the birth of the universe perhaps. Back then, the cosmos was unrecognisably different, orders of magnitude smaller and therefore more compressed, with its contents burning at more than a quadrillion Kelvin. Though it might not sound like a suitable environment for birthing a black hole, all the mass of the modern-day universe would have been crammed into a volume more comparable to the size of the solar system. and as ripples coursed through this ultra-compressed superfluid, tiny pockets of the highest concentration may have been sufficiently dense as to experience a gravitational collapse, yielding a class of so-called black hole unlike any we see today. A microscopic, primordial black hole. Primordial black holes are an unevidenced, hypothetical type of the early universe which would have existed on Planck-like scales, far smaller than both the stellar, intermediate and supermassive. First tabled back in 1966, they are postulated to have begun forming only a second or two after the Big Bang, within the most minuscule pockets of compressed primeval energy. Notwithstanding their 150 million year head start on stellar black holes, however, the primordial type also makes for an unrealistic candidate for the source of galactic engines. For reasons we'll come to later, their microscopic sizes and energetic surroundings would have rendered them explosively radiant, and thus incredibly short-lived, vanishing long before they could act as a seed for anything more substantial. Hence, neither exploding stars nor collapsing pockets of the primordial universe can be attributed to the beasts at the cores of galaxies. Something else must have given these black holes a supermassive head start in their growth. One generally accepted, albeit inconclusively evidenced hypothesis, is that these engines may have skipped the stage of stellar evolution altogether, collapsing directly into a black hole from the material within a gas cloud. The direct collapse model offers a plausible route through which the universe's largest engines may have gained the upper hand in the early universe. Within a giant, gaseous nebula of more than 50 million solar masses, certain physical conditions may prevent its fragmentation into star-forming pockets, instead causing the whole of its interior to give way to a singular body at the centre, so weighty that a supermassive black hole of up to 100,000 suns is born from the outset. Such a rapidly arising beast would have quickly assumed a central role in its emerging galaxy, requiring only sub-Eddington levels of accretion thereafter to reach the sizes we see today. As such, this explanation is an attractive one for astronomers and has been recreated in computer simulations of star-forming nebulae. The problem, however, is that the real-life prerequisites to form a black hole of this kind are so precise, they almost invalidate the very concept. In addition to needing enough material to form a whole cluster of stars, this gas cloud would need to be virtually metal-free, yet still somehow permeated by enough ultraviolet radiation to keep it warm and stop it from fracturing. Gas of this description would have existed sparingly around the universe between 100 and 250 million years after it was born, but in nowhere close to the quantities required to explain the sheer prevalence of supermassive engines today. And so, to find out what else built up these black holes, we need to look all the way back to this bygone age of star and galaxy formation, to a time when the universe's present-day engines were still in the process of accruing their vast masses, a challenge only the James Webb Telescope can rise to. The Webb Telescope is the most advanced space-based observatory we have, transcending telescopes like Hubble with its potency for detecting infrared radiation, as most of the light reaching us from the early universe has been shifted into those wavelengths. In mid-2023, Webb pinned down the properties of the most distant and thus oldest active galactic nucleus seen to date, residing at the heart of the galaxy Sears 1019, 13.2 billion light-years from Earth. It houses a supermassive black hole more than twice the mass of the Milky Way's, a staggering 9 million suns only 500 million years into the universe's life. Such a monstrous object so soon after the cosmic dawn implies that rapid, runaway forces hijacked this black hole's growth long after its formation from a dying star or collapsing cloud. In particular, a hierarchical series of mergers with other black holes, supplemented by brief bouts of super Eddington accretion, have been observed by the Webb Telescope as bolstering the masses of newly formed engines, culminating in beasts of 1 billion suns by only 1 billion years of cosmic time. We've known for the longest time that mergers have played an outsized role in sculpting the jewels of the cosmic web. Since the earliest, scrappiest dwarf galaxies arose from primordial ash, they have been colliding with each other and combining their stars and gas, climbing the cosmic ladder towards those established, enormous spiral and elliptical galaxies dotted around our local universe. Though the stars of progenitor galaxies almost never collide during a merger, it's a different story where two supermassive black holes are concerned. These colossal objects will inevitably seek each other out as their orbits become entangled in the core of the new galaxy. A Titanic episode then follows, where contrasting tidal forces scatter stars for tens of thousands of light years, catalysing a plethora of gravitational waves in the process. In May 2024, Webb saw this process unfolding in the ZS7 system, which existed about 750 million years after the birth of space. Within the disturbed heart of this tarnished galactic merger, two supermassive black holes of some 50 million solar masses each are circling one another as their orbits tighten, destined to collide later in the universe's life. Unfortunately, none of us will live long enough to witness its grand climax. But if we did, we would probably be able to isolate its gravitational wave signal using the upcoming Laser Interferometer Space Antenna, or LISA, a space-based gravitational wave detector for capturing the universe's earliest echoes. As such, it is hoped that ZS7 is just the start of a treasure trove of quasars and early galactic mergers just waiting to be uncovered by Webb, and then followed up by LISA for another angle of research. But even in lieu of its nail-biting finale, the ZS7 system still highlights the importance of mergers in growing the largest engines, providing a pathway whereby even the smallest stellar black holes can hope to reach supermassive stature. But given the amount of time taken for these events to unfold, it doesn't seem likely that mergers alone can account for the size of these supermassive black holes so early in the universe's life. Prior to their intertwining, they both must have spent the longest time accreting gas very close to their Eddington limits, perhaps even briefly surpassing them. Only last month, as of the release of this video, did scientists using the Webb Telescope home in on another supermassive black hole existing about 1.5 billion years after the birth of the universe. In November 2024, the galaxy LID 568 was jointly studied by the Webb and Chandra X-ray telescopes, as they spotted it undergoing a bout of super Eddington accretion some 40 times higher than theoretical limits, retaining its accretion disk all the while. This may be because the brunt of its luminous emissions are being carried off by a pair of relativistic jets, diverting and rerouting harmful radiation away from the disk, which would otherwise hamper the infall of material around the event horizon. Regardless, if confirmed, LID 568's super Eddington accretion may provide the final parameter in the complex equation of engine black hole evolution, allowing us to finally build up a picture of how the cores of the earliest galaxies evolved into the monsters we know today. Whether a small stellar black hole undergoing a proliferation of mergers within a cluster, or a directly collapsing seed from a massive gas cloud, these earliest supermassive black holes would have quickly come to dominate their surroundings, their initial masses allowing them to sink towards the basin of their host galaxy's gravitational well. And once established at the centre, these engines enjoyed unfettered access to their host's highest concentrations of gas, especially during galaxy mergers, which restocked them with abundances of new, invigorated star-forming clouds, alongside other engine black holes with which to merge masses. The chaotic accretion and convulsion of these interactions sends shockwaves cascading back through the interstellar medium, catalysing swathes of new star formation in their wake and sculpting the spiral arms of galaxies like the Milky Way. And it is for this reason that we call them engine black holes. As they churn out enormous amounts of energy, they act as a catalyst and regulator for the chemical evolution of their host galaxy's nucleus, while also playing a critical role in binding their innermost structures. As such, we can roughly relate the size of a galaxy's core to the size of its engine nucleus. And so to find the largest, we need to look within the universe's biggest, most star-bursting galaxies. And to find those, we need to look within the cores of galaxy clusters. Around the gravitational focal points of certain types of clusters, large volumes of intra-cluster gas and many smaller progenitor galaxies are concentrated into a single massive object, known as a brightest cluster galaxy, or BCG. A broad class of generally elliptical galaxy, which acts as the biggest, brightest, and most influential member of its neighbourhood. The sinkholes at the hearts of these great titans are among the most massive objects in the universe, reaping the benefits of their prime positions to accrue tens of billions of solar masses, reciprocating with some of the most energetic and enduring outbursts we've ever witnessed in turn. Lying at the centre of the Virgo A stretch of its namesake cluster, we find the BCG M87, containing the first black hole to have its event horizon imaged using the radiation of its surrounding disk. And if the 6 billion solar masses housed within this black hole is a cosmic T-Rex, the engine at the heart of the Abell 1201 BCG is a G-Rex, of a mind-melting 32 billion solar masses. Further afield, and black holes of up to 50 billion suns may be hidden beneath the blinding light of quasars. One of the crowning discoveries of the aforementioned Chandra Telescope back in 2005 was the detection of an ultramassive engine at the heart of the quasar galaxy 4C plus 74.13. In the throes of one of the largest eruptions since the Big Bang. For over 100 million years, this black hole has been burping the energy equivalent to several gamma-ray bursts a year, as over 500 million suns worth of material has crossed its event horizon. As a result, a pair of enormous cavities brimming with high-energy electrons have been carved into its surrounding intracluster medium, each spanning more than 600,000 light-years in length. It's difficult to reconcile such immense dimensions to a specific black hole size, but the most generous estimates today have it around the 50 billion solar mass mark. That is a whole 25% larger than the recently revised estimate for the former largest black hole in the universe, TON 618. Which was long thought to have a mass of 66 billion suns. But its recent revision of some 40 billion puts it more in line with a number of the other largest known BCG engines, like Holmberg 15A star, which anchors the heart of the Abell 85 galaxy cluster. Unlike the former, which had its mass derived indirectly from the properties of its quasar emissions, the Holmberg 15A engine's estimate was constrained with much more precision using measurements of gravitational lensing, placing it between 32 and 40 billion solar masses. In recent years, a couple of new candidates for the largest supermassive black hole in the universe have been touted. You'll likely have heard of the Phoenix A BCG engine, which did a whip round of the internet when a scientific paper proposing a new way to indirectly estimate black hole size flagged it as a candidate in the order of 100 billion solar masses. And the more recent arrival, re-evaluated from spectral line emission data recorded by the Sloan Digital Sky Survey, is claimed to boast more than 110 billion solar masses. Both these bewildering figures correspond to event horizons that would surely swallow up the solar system if replacing the Sun. However, it's worth remembering that both these estimates were reached indirectly, just like the 66 billion solar mass figure which had us exaggerating TON 618 for so many years. Generally speaking, most of the largest engine black holes that we can confirm with relative confidence occupy a ceiling of some 40 billion solar masses. Beasts of 50 billion may be possible, and might indeed be out there somewhere in particularly rare, massive BCGs. But much above this threshold, the sheer scale and time involved in growing them starts to become unworkable. But as the universe ages over the next 100 billion years, ultramassive black holes will have much more time to feed and merge, and engines exceeding 100 billion suns will surely come to be realised. But they probably won't be able to grow much larger than this, as the ever-expanding nature of the universe is constantly reducing the density and availability of matter, primarily by separating all uncollided galaxies. As such, these engines will fall dormant in the distant future, as their remaining gas fractions are exhausted and their resupplies curtailed. And as their host galaxies start to come unbound, only the universe's supermassive black holes will have the longevity for its longest ride, outlasting all other disintegrating structures as the final objects in the universe, with critical implications therefore on its ultimate fate. If the universe does not last forever, then neither will its population of black holes. If space has a positive global curvature, then its expansion should eventually come to a halt as it succumbs to its own self-gravitation, reversing the process and contracting at a point in the finite future. This will ultimately bring about the end of the universe, but not before presenting its surviving engines with one final opportunity. A shrinking universe will eventually reunify once disparate areas of space, bringing causally disconnected galaxies back within range of one another. In a snowballing process, the universe's engines would then begin colliding aggressively and combining their masses, with the rate of mergers climbing ever higher as space shrinks. Before long, most of the universe's black holes would be blended into a few overwhelmingly gargantuan objects, beasts of quadrillions of solar masses with such overbearing influences on space-time, they warp and deform the collapsing cosmos. Ultimately, as the universe verges on its primordial scales, all the matter of the entire cosmic web will have converged upon a singular, overarching, stupendously large black hole, with a mass far outweighing the 10 to the power of 53 solar masses contained in our observable universe. And with no other barriers or obstacles, space-time itself would fall into the black hole, tearing down the walls of reality and returning the cosmos to its starting state, a singularity-like point where the laws of physics break down. Thankfully, however, it doesn't seem that the universe is on a path to this kind of big crunch anytime soon, as the positive curvature of its gravity is being counteracted by dark energy, rendering a flat, smooth cosmos on an endless march towards its heat death. And in this scenario, after an incomprehensibly long while, the final crop of engine black holes will not merge, but will instead explode. To understand how, we need to incorporate the confusing domain of quantum mechanics, which considers the workings of space at a particle level, as opposed to the macroscopic, gravity-centric perspective employed by Einstein's relativity. In quantum terms, the near vacuum of empty space is awash with a collection of quantum fields, each one analogous to the individual strings of a guitar. And much the way a note is a vibration of the strings, a particle in quantum space is an aggregation of these fields' oscillating frequencies, also known as modes. But crucially, even in the absence of proper particles, these modes and their underlying fields still exist, manifesting as random energy fluctuations on nature's smallest scales. Like most particles, these modes can have positive or negative frequencies, and so broadly cancel each other out in the flat plane of undisturbed space. But when curved by the immensity of a black hole's gravity, the picture becomes much more complicated. And it is here that we would require a theory of everything to mathematically bridge the behaviour of particles and gravity as one. Such a theory has eluded scientists for over a century, but it was Stephen Hawking who conjured an ingenious single-use solution, which ultimately led him to the realisation that black holes leak their energy, and are therefore not eternal. When the trajectories of these modes take them within range of the black hole's gravity, their paths are twisted and redirected, and though some modes successfully skirt the horizon, a corresponding set of antimodes are lost, disturbing the delicate balance of empty quantum space. If these antimodes are negative, they will effectively reduce the black hole's mass energy as they fall beneath the horizon, as the addition of negative energy is tantamount to subtracting positive mass. And though nothing ever actually leaves the black hole itself, this lost energy must then be realised in the curved space outside the event horizon, as the near vacuum rewires itself with its revised set of positive modes. For a distant observer, photons would appear to be billowing from this reconfigured positive mode space, and it was Hawking who realised that this radiation would be thermal in nature, with a wavelength mimicking the black hole's Schwarzschild radius. What this means is that the largest black holes leak their masses in very long wavelengths and thus low rates of energy, whereas smaller black holes emit stronger, shorter wavelength radiation. And so, in the very distant future, when all other energies have been lost to entropy, the universe's surviving engine black holes will only be able to shrink as they slowly shed their mass, becoming ever smaller and hotter in a runaway process which reduces them to Planck-length scales. In their dying breaths, these black holes would then explode in a blinding eruption of light that scatters the last of their matter, reducing it to nearly homogeneous entropic dust. It will take an obscenely long time, maybe more than 10 to the power of 100 years for the largest black holes in fact. But in an eternally expanding cosmos, each of these engines will one by one depart in the most spectacular of light shows, leaving only perpetual darkness in their wake. And once the final cosmic bulb has blown, the universe will reach its heat death, as all remaining gradients between energy states are lost, and nothing can ever happen again. And on that delightful note, I wish you all a very Merry Christmas, a Happy New Year, and I'll see you in 2025.